Let's take a look at our homework that we had over the weekend, page 467, number 1 to 13. Any issues with 1 to 13 on 467? Anyone? 7, I heard. Sorry? I heard 7, 4, and 13. Going once? Going twice? Sold at 4, 7, and 13. Okay, 4 says, what's the effect what is the effect on impulse if the time interval is doubled, if the net force is reduced to 1/3 of its original magnitude? This is basically a variable value changing question, right? What's the effect on impulse if the time interval is doubled? Well, if my original impulse is f times t, we don't know what the number is, okay, but we know that it's f times t, then my new impulse, after I make my change to it, would be 2f times t. Well, we know what f times t is, right? It's the original impulse. So the new impulse would be twice the original. Does that make sense? We don't know what the original is, but we know the new one is going to be twice whatever my original impulse was. We're going to go through the same process to determine what the force would be. Sorry, the impulse would be if the force was reduced to 1/3 of its original magnitude. So we're going to say the original is f times t. We're reducing the force to 1/3, so my new impulse will be 1/3 f times t. But we know what the value of f times t is already. We don't know what its value is, but we know that it's the original value, whatever that was. So my new one would be 1/3 of the original impulse. Does that make sense? Okay, 7. 7 says, oh, look at that. Right away I see in 7b, I don't even know what they're asking in 7a or b, but I see a graph, an f versus t graph, in fact. So what's the first thing that should come to my mind when I see that f versus t graph? 3 words. Area equals impulse, right? Area equals impulse. As I read through this, from the graph below, what is the magnitude of the impulse provided to a 48-gram tennis ball that's served due south? Let's circle that in red, actually. Anybody go to Staples and get a crazy highlighter yet? It's Slurpee for the craziest highlighter, right? 48-gram tennis ball that's served due south, and what's the velocity of the ball when the bracket and the ball separate? So let's get the impulse first here. We know that the impulse is going to be found by calculating the area, and it's a simple triangle, so let's say the area is simply 1/2 base times height. Now we do have to be a little bit careful with our base. It goes from 0.5 milliseconds to 5.5 milliseconds. The base would be 5 times 10 to the minus 3 seconds. Right? 0.5 to 5.5 is 5, and it's 10 to the minus 3 because it's in milliseconds. The height goes from 0 to 900, so the height is simply going to be 900. What does that work out to be? We get 2.25 Newton seconds there. 2.25 Newton seconds. Now, in question B, we want to find the velocity of the ball when the racket and the ball separate. Now, let's assume it doesn't actually say what the initial velocity of the ball is, does it? I don't think it does. We're going to have to assume here that the initial velocity of the ball is 0. Okay? We don't know that it is. Yeah, we do, because it's served, right? Tennis ball is served. It's served from rest. So the initial velocity will be 0. We're going to find the change in velocity, which will be the same thing as the final velocity here, since it starts at rest. So let's get delta V. We're going to do that by saying delta P is equal to m times delta V, rearranging. I get delta P over m. I get 2.25 over a mass, which is 0.048, or we could say 48 times 10 to the minus 3. What do we get when we do that? We get 46.9 here, or we could round that to 47 meters per second. So 2.3 Newton seconds for the impulse and 47 meters per second for the final velocity. We've done quite a few of these questions now where we have these graphs. The one thing that I'll caution you on, okay, above what most of the questions we've done have involved, okay, every once in a while we see that graph that has part of the line below the x-axis. Okay, we haven't really seen that too much in our practice problems, so be aware of that. If you see a line below the x-axis, the only change you make is what? You got to subtract. It's got to be a negative value when it's below the x-axis. Okay, don't forget that. Everything else, pretty much everything else that you can be asked, we've seen quite a few times in our practice problems. All right, finally, the last one we needed to go over was question number 13. What's the change in momentum of a shoulder-launched rocket that experiences a thrust of 2.67 kilonewtons? That's 12. Yes, you're right. Oh, that's a good question, 13 is. Experienced curlers know how to safely stop a moving stone. What do they do and why? Who's a curler here? Anybody curl? Yes? How do you safely stop a curling stone? I curled a couple times in my life. I'm not very good. It's much, much harder than it seems. Okay, you put your foot out and stop it, but you don't kind of like put your foot out like this and keep your knee rigid and whatever, right? You kind of cradle it, right, as it's stopping, right? Those curling rocks are 20 kilograms, which is about almost 50 pounds. They're heavy. Okay, and sometimes they can be moving at a pretty good clip. Okay, they have a lot of momentum. They have a lot of momentum. It's difficult to stop those things. So when you go to stop it, you don't want to stick your foot out and just keep your leg rigid so that it doesn't have any give to it. Okay, the impulse of that curling rock is going to be the same no matter what. It has a certain momentum. It's going to have zero momentum. Okay, it's going to have the same impulse. If we can increase the stopping time by kind of cradling it with our foot, then it's going to decrease the force, which means it's going to hurt your leg a lot less. Okay. Make sense? Exactly the same question as the airbag question, exactly the same question as the goalie pad question, or cradling the baseball, or crumple zone in the car, right? The exact same thing. Okay. The odds are you're probably going to get a question like that, whether it's a curling rock or an airbag or a baseball glove or whatever, okay, on your test and then on your diploma exam as well. Good there? All right, on Friday we introduced with a video the idea of the law of conservation of momentum. We said that in an isolated system, momentum will always remain constant. What do we mean by the isolated system? It's important, obviously. We've got it italicized here. In an isolated system, the momentum will remain constant. If it's not isolated, all bets are off. Momentum may be gained or momentum may be lost. It's still not created, and it's still not destroyed, but you may lose some through the system, or you might gain some through the system. What do we mean by that isolated system? This is a Science 10 thing, right? Isolated system versus closed system versus open system. Yep. Nothing can get in or out. Yeah, can you be more specific, though? No matter can get in or out, but also no energy. And that's the really important one there, okay? We don't want any matter in or out as well, but the really important one is the energy. No energy in or out. In the end, we don't want any external forces. Okay, that's what causes energy to go in or out of a system, is external forces. Okay, if you have a car crash, two cars collide, and there's friction, okay, if there's friction there, then friction is an external force. Friction will take momentum away from the system. Okay, we want to have an isolated system where we don't have that friction, or we don't have that wind to add or take away momentum from the system. In an isolated system, in a system with no external forces, momentum will always remain the same. Now we're going to use this. Yeah, go ahead, Ken, question. Well, it's a good question. What's an example of an isolated system? There are no, it's difficult to have a perfectly isolated system. A professor of mine in university defined physics once as the art of making the right approximation. That was his definition for physics. And I kind of like that definition, actually. Because in the end, usually when we say we have an isolated system, we don't really. We're just approximating it as an isolated system. Like, say, curling rocks on ice. Okay, is there friction there to take energy or to take momentum away from it? Yes, there is, but it's very, very low. So it's close to an isolated system. That makes sense? Okay. If we look at a car crash, there's lots of friction, right? Not an isolated system. But if you look at immediately before, like a fraction of a second before and a fraction of a second after, friction really hasn't had a chance to do much. So we can say that is close enough to an isolated system, approximately an isolated system. Okay. So we're going to use this whole idea of the law of conservation of momentum to solve two types of problems. Collisions, which I think are pretty self-explanatory. Two things collide with each other, conservation of momentum, and explosions as well. What do we mean by an explosion? Well, we could mean a bomb exploding, literally. Something's blowing up. But we could also mean something like firing a gun. Okay, that's an explosion. The gunpowder explodes and the bullet goes forward. Okay, the gun goes backward. But we could mean something even less literal to that. You're standing on ice with a heavy ball and you throw that ball. The ball goes forward and you go backward. You are basically one with the ball. You and the ball were one object. Then it became two objects after you threw the ball. So that's like an explosion as well. Anytime we see two things hitting each other or one thing splitting apart into two or more things, then we've got a collision or we've got an explosion, and we can use this to solve the problem. Now, the last little comment here, I want to draw your attention to that here. It says, note that while the total momentum in an isolated system will stay the same, okay, as long as we have an isolated system, we won't gain or lose momentum in the system. We're not throwing out the idea of impulse. Impulse is defined as the change in momentum. An object that collides with another object will gain or lose momentum, even if it is an isolated system. Okay? But the system won't gain or lose momentum. So essentially, if we're looking at the entire system, analyzing everything, the total momentum will remain the same. If we're analyzing you, who's colliding with somebody else, you may very well gain momentum or lose momentum. Okay, but the system won't. Fire that gun. Okay, what's the momentum of the gun and the bullet before you fire it? 0. Okay, what's the momentum of the bullet once it's fired? Say 10. I'm making up a number here, but let's say it's 10 forwards. The bullet gained momentum, right? So did the gun. The gun had 10 units of momentum backwards. They both gained momentum, but the total momentum remains 0. 10 forward, 10 backward adds up to give me 0. Okay, so you can have impulse, but only when you're looking at individual objects. When you're looking at the system, momentum is conserved. How are we going to write this out? How are we going to mathematically state what we've just said here? The equation that we use to describe conservation of momentum is quite simply Pi equals Pf. Just like last year in Physics 20, we said energy, conservation of energy, was Ei equals Ef. Pi equals Pf. Now, all we have to do to solve this is replace Pi with mv, and mv for every object that we have. So, for instance, if we had two objects colliding with each other, two objects before the collision took place, then we would replace Pi with m1v1i plus m2v2i, and mv for each of the objects. If there were 14 objects colliding all at once, we'd add 12 more terms in there. M3 V3I plus M4 V4I plus M5 V5I, and so on. Usually, you're not going to have more than two objects before the collision takes place. Afterwards, PF, we do exactly the same thing. If two things hit each other and they combine because they both have Velcro on them, becomes a one object, then the momentum afterwards would simply be MVF, one term. But if two things hit each other and bounced apart like billiard balls, then we would say M1 V1F plus M2 V2F. Right? We put an MV in for every object that we have, both before and after the collision takes place. Make sense? Mathematically, these questions tend to be pretty straightforward, actually, pretty easy, usually. There's the odd one that's kind of hard, but usually they're pretty straightforward. The challenge in these is getting your givens written down correctly. Okay. Recognize the concept. Know that you're using conservation of momentum. Know that it's a collision. then write down your givens. That's really important here because there's so many different V's and M's and so on. Okay. Let's take a look at an example here. 9.6 on page 477, it says, a wooden block attached to a glider has a combined mass of 0.200 kilograms. So the wood block, the glider, 0.200 kilograms. Both the block and the glider are at rest on a frictionless air track. A dart gun shoots a 0.012 kilogram dart into the block. The velocity of the block dart system after the collision is 0.78. What was the velocity of the dart just before it hit the block? What's this? In other words, how fast did this gun fire this dart? What's the muzzle velocity of this gun? We're going to make this M1. Okay, that's going to be the mass of the block and the glider that the block is sitting on. They're at rest. So we're going to say V1I. The block and the block and the glider, initial. The block and the glider before the collision takes place. This is going to be M2 because that's the mass of the dart. This velocity, we're just going to call VF, not V1F or not V2F, just VF. Why? Why am I not putting the subscript there for the number V1 or V2, Travis? Yeah, they're all combined. We could call it V12F if you wanted to, because it's object 1 and object 2 combined, or we could just call it VF, the final velocity of the entire system after they've stuck together. Let's say PI equals PF, the initial equals the final momentum. How many objects do we have before this collision takes place? 2. So let's say M1 V1I plus M2 V2I. Let's put an MV in for every object that we have. 2 objects, they both have momentum. M1 V1I plus M2 V2I equals, how many objects do we have after the collision takes place? 1. So let's just say MVF this time. Not M1 V1F, but just MVF. The mass of the system combined times the velocity of the system combined. M1 is 0.200, V1I is 0, isn't it? I'm just Xing that out, actually. How come I can do that? If V1I is 0, then 0.2 times 0 is 0. If you want to show that work, go ahead. But whenever I have a term that's 0, usually I just X it out. M2 is 0.012 kilograms. We don't know what V2I is. That's what we're trying to find, isn't it? V2I, the velocity of the dart, initial. What M do we use here for mass? What is it? 0.212, both the masses combined, I think was a U page. Yeah, 0.212, which is both of the masses combined. They stick together. It's one object now. One object that has a mass of 0.212. VF, we're told, is 0.78. So let's do the math on this one. Pretty straightforward, I think. We do that math, we end up getting 13.78 meters per second, which rounded to 2 digits should be 14 meters per second. So just before the dart hit the block, it was moving 14 meters per second. Is that good? Is that a hard question? I think it's a pretty doable question, actually. Again, the big thing is getting those givens written down straight. Okay, what we don't want to do is, mix up V1I and V2I. Okay, don't put mass 1 with V2I. or vice versa. Okay, we keep those straight, I think we're good. I think if we keep those straight, a grade 9er could get this question. Let's try those two questions then, please, on page 477. All right, guys, if we have no issues with 1 and 2 here on 477, let's go to another one. This one says on 478, says a basketball player in a wheelchair, player A, have a combined mass of 58 kilograms. She moves at 0.6 to the east, pushes off a stationary player while jockeying for position near the basket. Player A ends up moving 0.2 meters per second west. I'm going to circle this. It's not a strange unit. There's nothing odd about the units or anything like that. There's nothing odd about it at all. It's west, big deal. Except that we know that we've got to make it a negative value. Okay, if east is positive, then west is negative. Okay, and I want to remember when I go to actually plug my numbers in that it has to be a negative value. The combined mass of player B in her wheelchair is 85 kilograms. What's player B's velocity immediately after the interaction? This is just my little thing. Okay, you don't have to do this at all, but I don't like calling them A and B. I like calling them 1 and 2. When I'm putting subscripts down for my, for my givens, I don't want to call it MA. I want to call it M1. So I'm going to say that M1 here is 58 kilograms. You want to call it MA, that's fine. She moves at 0.6 meters per second to the east. Clearly that's a velocity, right? But what velocity is it? Is it V1 or V2? It's V1. Is it V1I or V1F? It's V1I. It's the initial velocity of player 1 or of player A. She pushes off a stationary player, player B. We're going to say V2I is 0. Player B has a mass, player 2 or player B has a mass of 85 kilograms. Player A ends up moving at 0.2 meters per second to the west after the collision. What's that going to be, V1 or V2? Player A ends up moving that speed. We're going to call it V1, V1I, or V1F? V1F, because it's the final velocity of player B. I'm going to actually write down the number there. Again, to remind myself that I do have to put that negative in there, okay? We want to find player B's velocity immediately after the interaction. So we're looking for what? V1 or V2? V2, V2I, or V2F? Good, V2F. That's what we're looking for. So there's lots of things here. Again, 4 different V's, 2 different M's. We got to keep those straight. If we do, we're in pretty good shape for solving this question. So PI is equal to PF. How many objects did we have before this collision took place? 2. So let's go 2 objects, 2 terms. M1 V1I plus M2 V2I. How many objects do we have after they? 2. Remember in the last problem, they stuck together. So the term afterwards was MVF. This time, because there's 2 objects afterwards, we're going to say M1 V1F plus M2 V2F. M1 is 58. V1I is 0.6. M2 is 85. But I'm crossing that off. Why am I doing that again? Because what? They're stationary. V2I is 0. So M times 0 is 0. M1 again is 58 kilograms. V1F is 0.2 meters per second. M2 is 85 kilograms. That's V2F, right? Is that right? Somebody said what? Yeah, I left the negative off on purpose. You even see that I left a space there to put the negative in later on. Okay, but good for you guys for noticing that I left that negative. Okay, we may forget to do the negative even if we circle the west and write down right up here that it's a negative 0.2 meters per second. We might still forget to do that. It's a fairly common mistake, but we're a lot less likely to make that mistake if we draw our attention to it, if we circle it, if we highlight it or do whatever. Okay, let's do the math on this one now. I'll pull out the calculator for this because it's a little bit more complicated than the last one. We're going to say 58 times 0.6 on the left-hand side gives me 34.8. Now, let's add to that, use some brackets, 58 times 0.2. Why did I add that? I'm sorry? Yeah. It is. It's the same object, though, right? We're adding the initial moment, the final momentum here to the initial momentum, taking it over to the left-hand side. Mac? Yeah. What do I have here? Okay, I've got 58 times negative 0.2. It's a negative value. Okay, I can subtract that negative, okay, or I can just add it, and it ends up being exactly the same thing. So that gives me 46.4. Now let's divide that by 85 now. We get 0.546. 0.546, or we would round that to two digits, 0.55 meters per second. And I think it was positive, wasn't it? Yeah. 0.55 meters per second. Is that good? Exactly the same thing as we did in the first question, right? Except that we got an extra term here on the right-hand side. Okay, the last question we had one term on the left-hand side, we had one term on the right-hand side. The algebra was a little bit easier. Yeah, but even still, this is still grade 9 math, right? Once we get our numbers into the equation, it's grade 9 math. Question? Now player A is going to the east, right? 0.60 meters per second to the east. On the bottom one, it says that's final. Yeah, that's the final. That should have said a negative there, right? Yeah, is that what you're saying? Yeah. Yeah. I think because they have the arrow labeled, I think that's kind of their way of saying it's. In the end, you don't really need two different ways of saying that it's to the west. Okay, if you have the word to the west, or you have a negative, or if you have an arrow, any one of those are good. I put the negative in there because I didn't want to forget to put it into my equation. But technically, that's still correct notation because they've got the arrow showing it to the west. Does that make sense? Okay, your homework for tonight, Mel's going to go, if it goes today, it's going to go in a couple of minutes here. Your homework for tonight is simply the practice problems on page 478. I think there's two of them. Practice problems, page 478. Okay. Got a chance to work on those for a couple minutes right now. Finish them up for homework tonight, please.